Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have our lecture 6, and lecture 6 now brings us into the realm of machine learning, deep learning as a new term. And then we will also learn how machine learning and deep learning are related. And also, of course, in the course of HPC, we are most interested in also why now they can leverage essentially the GPU so much that we had the last time. So let's dive into the lecture of what we had in lecture 5, because this was all about accelerators and graphical processing units. And we had lots of basics in this, coming back to the many core architecture that I don't have here even on the slides. You remember we have very many cores in one chip that is basically not the cutting edge CPU that you know. So it's not high single thread performance, as you would say, but let's say moderate performance. And the key is, as you see here, a little bit elaborating on the architectures of an A100 here. That is basically then essentially having many of these cores, but in a moderate scale. So then also what we realized is that by far GPUs, as a special form of accelerator, if you want, have been now entering the top 500 list. So each of the different supercomputers that are there listed in the top 500, especially in the upper one, you see here, has some form of a GPU, and it's used for GPU, so general purpose graphical processing units, right? So this is the idea. With the idea of having a GPU now, we're not interested all in graphics suddenly. The idea is to use them for general purpose computing, because some of the tasks, as we learned also, are nicely parallelizable. I don't repeat that here now. We have been through this quite since the beginning of the course. What is massively parallel, what is nicely parallel. And here we have good examples of many problems we can, parallelize on a GPU very nicely. The other thing you learned is that we have different vendors. Obviously, in the past, NVIDIA A100 cards, nowadays H100 cards are really the, let's say, market share. But what we see more recently is that AMD Instinct cards, so from Cray and HP, are basically following suit. So you see here the top 10, basically from last November. The top 500 list always gives basically the list out in June and also in November. So there are 2 times updates per year. What are the, let's say, most performant HPC systems in the world that are known to this list, right? So, and in one respect, we don't know those that didn't submit anything to the list. So there could be something very hidden somewhere, which is maybe of much more importance and much more performance. But we don't know. So these that have been submitted to the top 500 are known to the world and basically also have this certain ranking. And you see here that the United States are quite prominent. The couple of first, let's say, are really just United States. And interestingly enough, many of them are also now with AMD Instinct cards. Of course, NVIDIA Grace Hopper cards are one of the most cutting edge cards from NVIDIA. Are also following suit. You see here Eagle, for instance, from the United States. And for us, it's also now very interesting that you have several ones which are then, also within the European sphere. You see Italy, for instance, or also Switzerland with the Alps system here with a Grace Hopper card, but also then essentially Finland, which is a Lumi system where also Iceland is a little bit in. So you can continue and and would say, okay, there's also Leonardo, which is a Euro HPC system, basically from Chineka. And this is something also where we see it's quite a race, if you want. And the race was sort of a specific element in the last, let's say, 5 to 10 years, if you want. So because everybody was looking towards exascale performance, and one of my earlier lectures, where the flops came from. So basically, this is a floating point operations per second. And the key message to take away is here that basically in 2022, we had really the first known system, right, in the top 500, which was a so-called frontier system breaking this particular boundary, right, of having, let's say, 1.1 exaflop. Nowadays we see here it's 1.6 exaflop, and we also discussed last time that there was a supercomputer called Summit that you see here, and the architecture is known here. That was quite cutting edge, was having 6 GPUs per node. And, we had seen like 25,000 and more than this within the whole system. So rack by rack by rack. And nowadays we have even basically decommissioned this system in a sense. The Oak Ridge laboratory that hosted the system has basically, removed the system. So even it was the most powerful in 2018, 2019, filling the top 500. We see now that after 5, 6 years, the system had older cards, so it was time to remove it. It had actually 6 Volta GPU cards, right? So per node. So lots of older technology, if you want. And now we basically see that the new system that was coming to Oak Ridge, right, after it was decommissioned, the Summit system, is now the Frontier system, which broke, let's say, in June 2022, which is already, a couple of years ago now. And we see that it's not anymore the powerful system anyhow. So now we have El Capitan and Lawrence Livermore. So hence there's a quite, let's say, momentum in the top, let's say, 10 of the top 500. When it goes lower down, obviously systems getting a little bit more settled. It's not this, let's say, big race about the big machines, if you want. And interestingly enough, you see, although here and there we see quite a dominance of the United States, of these big countries that have, let's say, lots of money and lots of national labs that you basically see here represented very well. So the first is Lawrence Livermore, then we have Oak Ridge National Laboratory, and then the third is Argonne National Laboratory close to Chicago. So these are all national labs of the United States, and they have quite some money for it. But interesting enough, still European systems are in the game. So Lumi is one good example that is now part of the top 10 of the top 500 since quite a while now. But apart from this interesting ranking, which some people would say is rather a political ranking, so without any more comment on this, I would just to say that some people believe that the performance of a system should be more on application benchmarks, not just the top 500 list. But this is a topic I don't want to raise now, but is of course an important view. And you have seen also in the top 500 the different, let's say, illustrations or statistics you can really derive from the top 500 list. So what are the vendors, what are the share of the accelerators, and so on. So in one respect, I want to summarize the lecture. Then finally, also the programming models. This was basically characterized that many of the GPUs, especially the older ones, maybe starting from Pascal and then going up to Volta, Ampere, and so on. They all have this, let's say, drawback that you always have to have the host CPU, fueling the device GPU, basically memory with some data, and also the instructions that are then handled by the scheduler in order to do some form of, if you want, shared memory program within the, let's say, accelerator. So it executes a so-called kernel and all these different many cores that you have available, depending on whatever card you have. This was a general assumption how it works. And then after the work is done, because the work is, of course, essentially done writing back to the device memory, right? You read from it, the initial values. You do your simple operations, because mostly these many core systems are fueled with thousands, but simple operations, not number crunching like we would have in CPUs. And then you write back the results to the DRAM, and then you get it back to the, let's say, host memory and report the results. So hence, sort of an interesting way to program it. And the kernel is usually programmed in CUDA, or as we see nowadays with AMD Instant cards, also with, let's say, ROC, and maybe even here and there with HIP. We have at the end of the last lecture, on lecture 5, also discussed some standards. But of course, CUDA is developing very quickly from NVIDIA, given its market share, the money investments. So hence the chances that standards, which, like HIP and so on, we discussed, are a little bit out of date, and to get the cutting edge out of a new card. And we discussed also Blackwell coming, right? A new NVIDIA generation, and also the, let's say, environment around it, which I would look close now with the NVLinks, that is basically the cards on a memory are very well connected if they are on one node here with the NVLinks. Hence, final statement, I could talk probably a whole course on GPUs. We have no time to do this, so let's have a very quick introduction to deep learning. And this should be in no way something where you should see that everything is so easy, right? So if I want to teach you deep learning, I need a whole course as well. So hence we start here with very fundamental basics. What are artificial neural networks? What is a neuron? Have some more application-oriented approach to it that we carry through to some of a very specialized way of doing deep learning called convolutional neural networks that we already introduced early in the course. So to make it a bit quicker. However, I think it's essential to have the basics. So what is a perceptual learning model is one of the first we will start in this part. And then having a very simple application alongside, which is the handwritten character recognition and this data set. And then we will advance from this, let's say, linear learning model to nonlinear, more fancy, if you want, artificial neural networks, which are fueled by backpropagation of error, an algorithm that make ANNs successful in the past. And of course, then we will, with this, also discuss a little bit why the computing is increasing. So why we need more and more computing. What is a GPU now bringing us as a benefit? And of course, here and there, some machine learning insights, also including overfitting or what is a classification approach and so on. In the second part, we will then turn to deep learning, but also there are transformer models, autoencoders, and whatnot, large language models. So here we're talking about one very specific architecture called convolutional neural networks, relatively simple and easy to understand. So we will have some of its, let's say, characteristics, going over the data, creating feature maps, understanding why data is suddenly instead of 1D, 2D, or even 3D, if you have a 3D convolutional neural network. And at the end of the second part, you should also get more and more sensitive to the idea of hyperparameters. So these are not the trainable parameters. Hence, the parameter term is now very important. The trainable parameters are the weights that you have between the different neurons and different layers and different feature maps and so on. There's also certain hyperparameter complexity that you have. Switching then to different optimizers, thinking about how many layers you really need, for instance, in a complex deep learning network, or what the learning rate is, which is, let's say, associated a little bit with the optimization techniques. And overall, we, of course, want to understand why we do this. And of course, the accuracy improvement is one key that we want to establish here as a yardstick, if you want. So why we actually go into deep learning, right? So what's the benefit? And of course, on the other hand, we also want to understand as a university lecturer, well, can we do everything with deep learning? So is there always 110% performance when I have an application problem? So do I need physics anymore? And things like this. Hence, after that, you go a little bit away from perhaps a deep level of parallel programming, much more to a parallel computing on using, let's say, libraries like we have, in this example here, TensorFlow, Keras, but it is very similar in PyTorch. So you have basically idea of parallel computing on different levels. Of course, underneath will be still different elements where we will discuss in the next lecture also how we come to distributed deep learning, then going back to HPC a bit more. And then in one respect, you have also with this directly foundation approaches to scientific domain specific application, especially those, of course, that are going to AI. But today we have also here and there maybe some links to examples, and research also is basically focusing now on something we call physics inspired deep learning or physics constrained deep learning, physics informed deep learning, though there are many words around the fact that maybe combining the power of physics formulas with AI might be a good case. And a university course like this cannot go into it, but I would point you to the CU Race project that we had that was already exploring in research some of these aspects. So we really put the focus a bit on programming today. And of course, this means programming in AI, but automatically having also, let's say, a HPC programming paradigm of using really GPUs. And next lecture will be then also using these GPUs at scale. So let's start with artificial neural networks. If I would be in class, I would asking you now, so who has anywhere heard about it? And I know some of you have taken already the machine learning course, so you have a little bit an advantage now understanding some certain things. And to get a very practical introduction, because we have not much time to cover this topic, I would, if you're interested in this, rather point you to our machine learning course in the university and our deep learning courses. So let's have some more application-oriented approach, and we call that a bit here supervised learning as one of the ideas of learning approaches. And the idea why it is supervised is that we have certain input data, a vector with different values. And for each of these values, we have a given output that we would expect. So we have a guidance on saying, okay, this is what we want to have out. Hence, for every data element that we have a vector, which lots of having maybe different features in the data. And we understand it is in class A, class B, class C, and so on. So the output, in a way, in an abstract mathematical formulation here, acts as a supervisor to really give us guidance in the learning process. Do we have the right, let's say, learn done, or should we go back and maybe revise our model? So there are different ways also why you want to do this. So there's a sort of prediction that you want to have some, let's say, future observations, and you want to classify them rightly, or you have an inference that you basically understand much more the kind of response when you have a sort of predictor. But the key message to take away is really that you have this input data, but you have also the correct output data, which makes it supervised. So in unsupervised learning, you don't have that. You have just the input data, and you have to help yourself if you want, maybe through Euclidean distances, measurement measures, and so on. There's also reinforcement learning that then works with, let's say, a little bit like penalty and reward systems, agents, a little bit more like gaming if you want. So there are different ways how you can do learning from data. Let's have a simple example. In the given time we want to have this flower classes here, Iris setosa, Iris virginica. We have 100 samples available. And we see here when we plot them that, some of them are basically the Iris setosa, the green ones here, and the Iris virginica, very clearly separated in the space. Now, the point of machine learning is we want to have future data, correctly classified. So we don't interested in this data that we have. That's where we learn from. But what about this data, flower? And when I ask now people in class, they would say, is it setosa or virginica? I had just one in class after all these years and trainings I gave that could answer this, because you have a petal and sepal width, and you see indeed in the flower then maybe certain characteristics. But for a normal human, if you want, not being so flower inclined, would be this a quite interesting question. So given on this picture, what would you think? Is it a Iris setosa or Iris virginica? Hence, when we have a new point, what is here, with 7 given characteristics, we want to have established a learning model, which gives us sort of a decision boundary. And this is now an important term in machine learning, where we can decide. So everything above that would be Iris virginica, and everything below this would be Iris setosa. Hence, we motivate here now the simplest learning model that you can have, the perceptron learning model, which essentially gives you a linear learning model, linear in space and in the weights. So we want to have essentially a line in space that is now separating the decision space with the decision boundary. Now, when you model this, you can see a line in space is nothing else that we see here. For mathematical convenience, we put the bias a little bit, the part where you can shift the line in space a little bit into the learning model with W0. Otherwise, you would have a plus something here. But we also make it as a learnable one, and we sum up linearly this weights. And the interesting thing is why I mark this red is that these are the learnable parameters, right? So X is a constant, right? This is important because this is our data set. Then we would have a nonlinear activation function. I introduce this now because basically later this will be a key idea to understand now why the perceptron, although we have this linear combination of the input data, linear and weights, right? So this is not everything, right? We have these summed up linearly using weights, but plus a bias. but we can still put them through some form of an activation function in order to make this right. And then for mathematical convenience, some of you that are a bit more mathematically inclined will know this. We can do X transpose W to make this as a vector, and basically the transpose of it, which looks a little bit like this. These X still are constants, our input data, and then the trainable weights that we have as well, and then becomes more or less a dot product here. Then for an application example, I took here an example which is, let's say, 10 digits, 0 to 9, to classify. It's a well-known so-called MNIST data set. I'm sure some of you may have heard about this before. So essentially, we want to have handwritten digits, and we want to classify if, the handwritten digits equal what we would think. The truth is that there are 28 by 28 pixels, that there's around 60,000 of them as training samples and 10,000 as test samples. So these are two names which are also very important for you. We will come back to this in lecture 6 and lecture 7, and also later when we talk about Reza's lectures. We implement this a bit with Keras. You see this below here. Essentially, Keras gives us the opportunity to load this, let's say, benchmark data set or this training data set really quickly from MNIST, and it automatically gives you the training and the test set where you can work with, that you see here below. So quite convenient for us. So hence, long story short, we have the data. It looks like this, right? So when you now plot it a little bit with Python, you have this handwritten characters, which are then, of course, grayscale over, a space, which sort of is a painting. And you can see it might be a 5, this might be a 0, this might be a 4. And what makes it now supervised is that we have a label. Now, we see there's not only this 2D information that we have, there's also one guiding label Y that says then Y equals 5, Y equals 0, Y equals 2, and so on. We also have many of those, as we learned, but there's a cut in the training samples, as you learned. There's so and so many in training set and so and so many in test set. So it is tough to say how much you really need for training and test. It's an application domain aspect. There's a rule of thumb. Sometimes the more your training set is there, of course, the better the model. But in order to be, let's say, accurate, what you predict in real practice, you want to have also the testing data set quite large. So it is a little bit, you would say, an interesting question where you do this cut, but you need to do the cut in order to validate your model. Bring also another word into the game here that I just want to talk about. There's a validation set you usually have that you use for model selection that I cannot really cover much in this course, because this is an advanced machine learning part where you would say you do the training, then you evaluate your training results on the so-called validation set. You pick the model that is most effective. You introduce a bias in the data, an optimistic bias. Hence, the validation set should be thrown away, basically. And then you use a test set for actually checking your final performance. So there are tricks like cross-validation in order to, do similar things. When you don't swim in data and you don't want to throw away your your validation set, but we don't cover that too much here in this course. Here also, I would like to link you to the more insights of a proper machine learning course, or one of my earlier, let's say, courses I have in training, on 3 days or so on deep learning completely, that you find on YouTube as well. And these are fundamentals, right, in machine learning. So it's not changing very quickly. We already learned the Python packages, so TensorFlow and Keras. So I would like to, skip this a little bit just to let you know that the next scripts that you see are a little bit in Keras and underlying then executed in TensorFlow. So the first script you see is more or less a data exploration script of the training data, a bit like what you have seen before. So how the data looks really like when you put it in a Jupyter notebook, for instance, a Python environment where you can execute interactively, let's say, some Python code. We introduce a data set here with Keras. We need NumPy as a Python library helping. We have this data set now loaded, as I was alluding to before. And the simple function we have here as data exploration script is nothing else than going essentially through the characters that are essentially the space that we have for each of this training set and also test set. Hence, if we call this character show with a train set on a given, let's say, index or range, we could do the same on the test set. It will not look different. It's the same sort of idea, right? That we have this kind of different 2D problem, and everyone has a guiding label Y. So it's a small helper function if you want to see a little bit how this works. If you now do this, let's say online in Jupyter Notebooks, or maybe even in different public clouds or in Google Colab, always take care a little bit of the environment you're in. You need the right packages to be there. And this is an important element. Coming further then now from the perceptual learning model idea, so how we learn from data. And this is an interesting fact because this goes back to the very early beginnings of machine learning. So the perceptual learning model that you see here is firstly a linear learning model. That means linear in weights. And you see that here with W0 to WM. In other words, we have a 2D problem here, which needs to be filled in a problem space or in a model space, which is one-dimensional. Hence, we call that reshaping. Some of you are really maybe in numerical simulations or have been learning about this a bit more. They know also they would call it sometimes vectorizing, right? So you would say instead of having this 2D matrix, if you want, you have one long vector, 1 to xm, which constitutes your data. And usually in class, I would ask, so what's the problem now by doing this? I have a two-dimensional data set that I force to be one-dimensional. And this is a good question, I know. There's always one or two people in class usually that would say, yeah, you basically miss a context, right? So basically by vectorizing, we have some context, of course, data before and after, but we're sort of losing, you see that a little bit, especially in the characters here, when you have the, let's say, more grayscale data, the surroundings. From 2D to 1D, you have just one long vector. And this will be a key essential part to understand deep learning later in the second part when we keep the 2D structure. But for now, to put it, let's say, in the simplest learning model I can give you today, we have to vectorize it, we have to reshape it, and then for mathematical convenience, we also have to normalize it because, of course, with this grayscale, you see here quite high number values. If you multiply them often, what essentially learning will do, you remember when I said learning means often matrix multiplication, matrix vector multiplications, the signals getting strong and stronger or weaker if you don't multiply, or maybe gets lost when we do weight decay or, weight drop, things which are all advanced regulation, let's say topics which I also need to, link you to a proper machine learning course. So there's different aspects that I cannot really, in the time given to me here, focus in this course. But the key message to take away is now that the same data, more or less, is now encoded here in this kind of very long vector, right? In terms of 2D, we have 1D. And we do this with a test sample and the trained samples, of course, and we normalize them in order to have the numbers between essentially 0 and 1, so that we multiply them often and so on. We'll never get a, let's say, out of bounds problem of out of, space in terms of integer value. So hence we understood this is a loss of information, but still it gives us the opportunity to use one learning model, which is the perceptual learning model that stands the test of time essentially, because it's still in one respect really integrated in the models we have that are cutting edge. Because the idea of a neuron that mimics now the human brain a little bit, of having different inputs of the left side, and then we learned this summed up linearly using weights, put them to a sort of activation function, and then get some output probabilities, stays with the idea of artificial neural networks, hidden layers and so on, but also later on in deep learning, they are really exactly analogies to this neuron as well. Hence, it's a simple Lego building block, if you want, in order to understand this. And what we really learn is that every one of the input parameters is now essentially, connected to and this makes it this sort of dense layer, which we also learned to learn in the second part, is not always the case. But in our simplest learning model, we need this, and this is what we learn and what is computational. Now the question to, basically compute. You see the code on the right side. So how to do this in Keras? You have a sequential model, meaning you add a layer by layer, and you have a dense one from the number of classes. So this is now very important to us. And the input shape, which is now the reshaped long vector, right? And this gives us essentially now a fully connected layer. And we add the softmax activation function that gives us now the idea of having this different output probabilities. And because we have this number of classes 10, we essentially do this, with the neurons essentially in one of the idea here, to have this always put through the softmax activation in order to arrive at some, kind of, you would say it's more a probability if it is now a 5, if it is a 9. It could be also an 8 because it looks very similar, right? So in a way, that is important for us computationally now. For it's important, and Keras gives this out, that we have now sort of 7,850, right? There's no secret. We have 10 classes. We have input parameters 784, so times 10 plus bias, right? Then we are quickly at the idea of, 7,840 plus 10 classes with its 10 biases, giving us 7,850 parameters to learn. This is not so much compared to many others, but of course already needs computational complexity. The way is now we learn is about optimization techniques. We use here the stochastic gradient descent technique, although there are also more smarter versions like Adam or, Nemestor's momentum and so on elements in it. So here we essentially take the gradient of a certain loss function that we can define essentially. And in the idea of having this kind of 10 class classification, I in the moment put a categorical cross entropy loss, which stand the test of time for those, let's say, problems where there's a categorical problem. So from 0 to 9, for instance. And in order to basically optimize it over time, we will always have, take a gradient essentially from our, learning progress and evaluate it then to the loss function and go basically one step further, iteratively through this. So again, it's quite interesting, quick go through how deep learning works. And you don't do this one time, you do this, let's say, in many epochs, given different batch sizes. So there are different parameters really that you define in order how to do it. You pick the optimizer, you see that a bit here in the class, and to do stochastic gradient descent. And then you have basically the code here that we already discussed. We reshape the 60,000 training samples, the 10,000 test samples to be, let's say, more mathematically convenient in one array, one long vector, to be fitting to the perceptual learning algorithm. And then we essentially normalize here a little bit to have, this for mathematical convenience of the learning. So hence we put this all in 1D problem if you have the source code. And then we have the sequential model here. We add this kind of dense layer with a softmax probability of saying, okay, it should be between 1 and 0 and 9 if you want, 10 classes that we defined above as a constant. And this remains, for instance, for a long time, even in convolutional neural networks, we will find this again, softmax layer. So we will come back to this. And then we have a model summary plotting us a little bit how the model works. But really the optimization then will use the optimizer like Adam or SGD in our case will have a certain metric of accuracy and will also have the loss function, which is a categorical, let's say, cross entropy loss function that you basically use then to evaluate if you're really better over time in learning. You put this all, as you see here, in the model fit function, xtrain, ytrain, so basically the labels, right, for the training model, the vector x for the training, how big should the batch size is, so often I go through the data in order to reach one epoch, and then, some output, and you model then the evaluated score, and so on and so on. So you see how that works, and I give you also some ideas here that this is sort of an algorithm already with this kind of efficiency, which or accuracy, if you want here, is already 92%. So we talk about it is quite good already, right? It's a very trivial problem that we have with no hidden layers. So basically a simple neural network, if you want a multi-output perceptron, as we call it, it's not a simple perceptron because we have not yes or no. In a typical machine learning course, we would start with this. Here we have already started with a 10 output perceptron, 10 classes. So it's a bit more elaborate, but it still captures the essence what we do. And now there are, of course, different aspects that you have to understand in machine learning. Also very important because, I talked about you with validation and regularization, which basically combat overfitting, but there are different parameters to choose in order to take the optimum. If you learn too well and memorize each of the different dots, that's not good. If you have a function which is too simple, that then gives no, let's say, feedback to what you learned really, it's also too little. So to find the optimum is not so easy, right? So you will see that usually error on the training examples will go down of the number of iterations. You're basically iteratively changing the weights, update the weights, and get them proper to the learning problem. And you can follow suit with the error on the test samples. But at some point in time, you will see that even if you continue learning and learning and learning, you will overfit, like you see here again, where you start memorizing how the data will look like and you don't learn. Think about an exam where you memorize maybe before you do the exam with a test exam, all the questions you had and you memorize. So this is not really learning, and you get a new exam and you don't know how to apply, the basic functions or the basic ideas of an exam from the terms of, learned material instead of just memorizing an old exam. So you essentially have memorized the old exam, but you don't really learn, right? So this is sort of an analogy, but it also shows you that now the question is with 92%, and it's a bit stochastic gradient. It already shows it's a stochastic process. So sometimes it's 91%. You can influence this also with a little bit of regularization and validation, but it will be staying in this category given this simple learning model. Hence, the question for us would be now, what can we do? What can we improve on this learning model? And I mean, here's now the key point to make it from a multi-output perceptron model to an artificial neural network. Neural network really stands for the fact that we maybe introduce more hidden layers, right? So that we don't have just, sort of zero layers, or if you want a kind of, directly input-output connection. So maybe we can have the neurons in certain layers. Hence, we come from, the linear perception model and its limits, and the limit is remaining in its linear learning model because you have just one line, and you have here the famous XOR example. This would be one data set that you can never learn really basically with one perceptron. Hence, the idea of the artificial neural networks is to combine different of these. So you see here, there's definitively, again, the same idea with input nodes summed up linearly using weights, put them through an activation function per node, which is our neuron, our perceptron, but use many of them in so-called hidden layers. The input layer remains and the output layer remains, right? This is Y. And this is our data set, our long vector now of numbers, not any more metrics that we discussed. Hence, it's not big magic. You just basically combine them, and instead of having this only weights that you have from all of these different input layer to one perceptron, you have suddenly a hidden layer with many of them. And this is now, of course, something which is important for us to understand, that we can choose how many of those. And then on top of it, to catch nonlinearities, what is happening in neural networks, and this is, of course, again, a little bit alluding to an advanced scenario, but you have to go to machine learning, courses a little bit, maybe if you want to understand the real details. But you put this, can say, linear learning then through a nonlinear activation function, which enables us now to create this interesting nonlinear boundaries that you see here, right? Otherwise, you would stay with this function and have a pretty good line. And you see that some of the data is maybe better classified of having a nonlinearity. Also, what is known sometimes catching nonlinearities with linear, let's say with activation functions that are well known, today that you see on the right-hand side, like the TANG, for instance, or the rectified linear unit, ReLU, and so on and so on. Leaky ReLU is also getting more and more popular, by the way. Anyway, so the goal is here, of course, that this is something where this is the architecture of the neural network, and that's something what you don't really know per se. So something that you have to pick. However, to also think about now the trouble that you have essentially when you come now to this hidden and second layer was solved before by the so-called backpropagation of error, because in the simple perceptron, you had always this feedback mechanism going directly back and see, you put it through, you had access to Y, and then you know, okay, Y was wrong, let's do it again. Now, what happens here in the learning, when you have now many of those hidden layers, you lose the connection directly to the error, right? This is somewhere on the right side. And the backpropagation of error based on the chain rule and other aspects I cannot, from the time-wise introduce in this particular lecture, is going and backpropagate the error so that you can update, the weights that you see here. That's the learning, right? What will take place based on this error in each of the iteration, giving, through the backpropagation of error algorithm. And that was a breakthrough also of artificial neural networks, making it from a, let's say, perceptron learning model to a multi-layer perceptron, or otherwise also called artificial neural networks, implementing the backpropagation. And then in the end, the rest stays the same. So things with the softmax, and then the winner takes all decision rules. So who has the most probability is probably also the best class estimate for a certain input X. So hence, it's a little bit elaborate to do this is backpropagation, updates of the weights, and then there's even a learning rate that you basically have to do when you do this gradients. But this is a computing intensive part now, right? We compute gradients, and we actually multiplied this also with a certain learning rate that we ourselves configure. And by doing so over time, we see the error surface here, of this loss function we go to the minimum, hopefully, over time, which is a bit like shown here, and updating the weights essentially every single time step by looking also what was the output Y, the guiding sample, and what we basically, have as a solution right now. The learning rate plays an interesting factor here. So if the small learning rate, we just, see here a little bit, we kind of start with an initialization and don't really progress. If you have a large learning rate, we're jumping and back and forth here on the error surface and never will find the minimum as well. So it's also sort of sweet spot to find the right learning rate to get then to this minimum we need in order to hopefully have the less error on this, let's say, loss function, to then have the best machine learning model in the moment that we can report and then hopefully use. So many of these points are obviously, let's say, quite quickly in this course. And I would say that's, of course, clear, and you don't have to maybe understand all the deep hidden aspects of it. It just basically is a HPC course. So you have to make the connection that, of course, now many of the gradients have to be taken if you have a large network. Now we talk about here not about 4 hidden layers, neurons inside of each, but rather maybe 150 or so. Right, you see here a little bit number of hidden layers, number of hidden neurons in one layer is 128, for instance. Hence, the weights will be much more in order to do this. The way how you program this is, however, not so difficult. You have a sort of dense network. We understood this. Not every one neuron is connected to the next neuron fully, with AVO connection, making it a feed-forward INN. Here, 2 layers. And you do the same, the activation function, because it's quite popular, is a ReLU, the rectified linear unit. And in the end, you have still, let's say, the softmax activation function giving you an output probability of this 10 classes, 0 to 9. So very similar. We just introduced sort of this now mesh of network and neurons here that we have. The rest of this stays the same, so it's 10 classes and so on. When we do this, execute this on high performance computing, we will see we improve to 0.97 because now the learning capacity with the weights is much more. An artificial neural network with 2 hidden layers is quite strong. If you have enough data, you can try and learn it, and it will be, let's say, quite good, as we see with 0.9%. So hence this is a new benchmark, but we have to pay the price for it, right? The multi-output perceptron was 92%, 91%, 20 post-trained. Now we have the artificial neural network, two hidden layers. And if you are, let's say, putting a bit regularization in and other aspects that you see here, we are a bit more realistic and now suddenly stand at 95%, which is sort of a good yardstick for it. And however, the price you pay, you see on the right-hand side. We have not anymore 7,000 parameters or something. We have 120,000 parameter roughly. And these need to be all learned, meaning all computational complexity. It's hence much more computation intensive to do this network. But I mean, we got a benefit of, let's say, 4%. Hence, the question is what we do in part 2. We try to better this with deep learning, which is already a quite challenging task. However, for the first part, I think we stop here and I give you a video that summarized quite nicely the idea of nonlinearities, of the connections and so on. So have a view on this and we will basically come back in 10 minutes with the second part.